Everyone, and welcome to the second lecture of series of the mini course of Professor Chirikian on the introduction to Don't-Care-Baradan large deviation principle.
Thank you very much. So we need to give some reminders of what we did yesterday. So as before, I know by X compactness. I consider a sequence psi n of n-squared random variables. And we introduce the concept of large deviation for this sequence. We said that we have a large deviation for this sequence n. This by large deviations for LDP. By definition, this means that there is a lower semi-continuous function I, which goes from x to 0 plus infinity, such that for any gamma in the Borel sigma algebra of x, you have the following: the limit, in fact, it's not really a limit, it's upper and lower limit, but we have to mention that, and we write like this: logarithm probability that psi n belongs to gamma is equal to the dot minus I of gamma. And by definition, this means that you have upper and lower large deviation bounds. So this means that we if an n goes to infinity of the same thing, logarithm 1 over n logarithm probability psi n gamma is minimized by minus I of gamma, interior gamma dot. So I of something is the integral of I on that set. So I of A is the integral of I on the set A, and so this is the large deviation lower bound, and then you also need to have large deviation upper bound. And goes to infinity. The same expression, logarithm probability psi n in gamma. These should be smaller than minus I on the coordinate graph. By definition, this equivalent in the dot graph means that we have upper and lower large deviation bounds. And then I formulated Baradan lemma. Then the following: if you have LDP for psi n with a function I, satisfies LDP with I, then for any continuous function, really continuous function of the space X, you have the following limit. The limit when n goes to infinity, 1 over n, the mean value of exponential n f of psi n. This can be written differently. This can be written as a limit as n goes to infinity, 1 over n logarithm integral over x. I'm using the change of variable formula or transfer formula for making integral exponential n f of x, and I denote by mu n the low of psi n. Right, so mu n is the low of psi n. So it is a measure of the space X. Then this will be equal to the sup, the upbound on X, or the difference f minus I.
There should be a logarithm, right?
Yeah, logarithm, yes, thank you. Logarithm of the integral. Okay, so this is what.
Sorry, for this lemma, you need x to be compact or not?
No, in fact, you don't need x to be compact, but you will need some conditions on f. But in this course, I will always assume that x is compact, so we can avoid this complication. So x will be always compact for us. Okay, then we have the following example. Which will be important for what follows. We have another compact metric space. And we consider the case when X is the space of probability measures on X. So I will always assume that you have a big topology, big star topology on Px. So Px is endowed with big star topology. Well, I wrote the base of topology yesterday, but in fact we will not need it. It suffices to know what this big star topology means. It means that if you have a sequence mu n, then mu n converges to mu by definition. If not by definition, because I introduced the topology. Mu n will converge to mu in the big star topology if and only if for any continuous function on the space X, the integral of v with respect to mu n converges to the integral of v with respect to mu. And a non-trivial result is that, again, we will not leave this result to the proof, but we need to try the validity of the result, which says that Px, the space of probability measures, in big star topology is detriable. So in principle, this is a logical space. And if you consider the space of all measures, all sign measures, binary sign measures, it is not detriable. But if you consider the space of probability measures, this is detriable. And in addition, there is another result, which is essentially Prokhorov theorem. Prokhorov, which says that this is in fact compact. So I will not write each time W star. Px will be always equivalent with V star topology. So Px is compact. Okay, so now let's try to see what this lemma is in this particular case. So suppose that we have a sequence mu n. You can think of a sequence I introduced last time. So last time you considered the sequence, the time average of we considered empirical measures, but it's not important that it's the empirical measure. Let's consider just any sequence mu n, which is a sequence of random variables with range in this space Px. We are exactly in this setting. Then, by Varadhan lemma, we'll have the following: for any v, which is a continuous function on x. Why I deal with continuous function on x? Because I can define a function on the space Px. I can define a function from Px to R, which takes a measure mu to its integral with respect to the integral of v with respect to mu. And then this big star topology ensures that this is a continuous function on Px. So for any function b, any continuous function b on the space x, define a continuous function from Px to R by just taking the integral. So I can apply another lemma to this particular situation, and it gives the following. Parallel lemma implies that if you have large deviations for mu n, so LDP for mu n implies the following, that for any v in Cx, there is a quantity QV which will call pressure. I will not specify where these terms come from. It's from theoretical value, but it's not important to us. By definition, this is exactly the limit which was written here. The limit n goes to infinity, 1 over n logarithm, and I need to take the mean value of exponential. Then I have n times v integrated with respect to mu n. Right, so this is exactly this expression. Mean value, logarithm of the mean value, exponential of n, f applied to psi n. F is my continuous function. Now it takes mu to v mu. Right, so I need to take just f applied to mu n, which is v integral with respect to mu n. And according to this formula, this gives you the supremum. I need to take the supremum over all mu in Px, and then f, therefore I need to take v mu minus the rate function. Okay, so in the particular case, when you are dealing with random measures, right? Mu n is a random variable, with range in Px, so this is a random measure. You have this quantity QB, by definition it's equal to this one, and Laplace lemma gives that this is indeed well defined, the limit may not exist, but if mu n satisfies one condition, then this limit exists, and it is equal to this one. And here you recognize what is called the general transform of I. What is written here is the general transform of I. Okay, so I only now subtract from comments analysis. Before recalling that, let us remark that QB, let us prove lemma, small lemma. This function QB, which is defined by this relation, is one Lipschitz and convex. The function which takes B to QB is one, so it acts on the space of continuous functions to R, is one Lipschitz and convex. Okay, so let's prove this result. It's not difficult, so I can present the proof. When we give it convexity, in fact, it suffices to prove the convexity of this one, right? Because if before limit your function is convex, then you pass to the limit, it will still be convex. So what we need to prove, let's denote this by, let's say, Qn of V. So we need to prove that Qn theta V1 plus 1 minus theta V2 is smaller than theta QV1 plus 1 minus theta QV2. Where theta is any number between 0 and 1. but this is very easy because the mean value of exponential n theta v1 plus y minus theta v2 integrated with respect to mu n. I just apply Euler inequality to say that this is smaller than, I apply Euler with exponent 1 over theta and 1 over 1 minus theta. It gives you mean value exponential and v1 un to theta and mean value exponential n v2 un to 1 minus theta. And if you take the logarithm, you get exactly this inequality. So this gives you convexity. And for one Lipschitz property, it's sufficient to prove that what you have here is n Lipschitz, right? Because then when you divide by n, you will get 1 Lipschitz. I should write here. So let us take two functions, v1 and v2. Then we can write qn v1. It is equal to logarithm mean value exponential. I write in the following form n v2 mu n and plus n v1 minus v2 mu n. So I didn't change anything. I just have here v2 mu n and the same thing v2 mu n with the minus in front. Now let's remark that this will be smaller than the norm of the difference. Of course, I take the supremum of the maximum norm of the space Cx. And when I replace this by the norm, you will get something bigger. And this is integrated with respect to mu n will give you exactly the same expression. So this will be the same thing because mu n is a probability measure. So this will be in fact smaller, right? This will be smaller than v1 minus v2. So now this is deterministic. I can put it in front. So what you get is the following: logarithm exponential n v1 minus v2, and then what is left is the mean value of exponential n v2 mu n. Right? I didn't touch the first term, and I replaced the second term by something which is bigger. So I got inequality, and now I logarithm of the product. And I take the logarithm, I get n v1 minus v2 plus, when I put this outside, when I apply logarithm to the second one, I get exactly qn v2. So qn v1 or n v1 v2, qn v1 is smaller than n times the norm of the difference minus plus qn v2, which means that the difference is smaller than n v1 minus v2. If there is no difference between v1 and v2, we get a Lipschitz product for qn, and therefore one Lipschitz product. So we divide by n. Okay, now let's come back to the complex analysis. So we have once again, so we had a sequence mu n which satisfies one deviation principle. According to Maradon lemma, this limit exists, qv, which is the limit of this expression, and by this formula, Maradon formula, you get this one. So if mu n satisfies LDP, so conclusion, if mu n satisfies LDP, then first QV is well defined, the limit convex only. The second point is that QB is the linear transform of I. And if by chance I know that I is convex, then the relevant result in convex only says that you can recover your function I using again the general transform. General transform is the involution. Well, it's not very correct to say involution because we are working on different spaces, but for instance in RB it will be indeed involution. In the sense that if I is convex, then you can recover I by the same formula. Essentially the same formula. You take the supremum B mu minus QE. Okay, so this is a well, we didn't do all this last time, but this one was a summary of what I wanted to do in the end of the last lecture. Now we'll need another property, which is called large deviation compactness. Large deviation compactness. Well, the fact that Px is compact means that if you have a sequence of measures on X, Px compact implies that for any sequence in Px, there is a subsequence, N1 smaller than N2, and so on, such that, and there is a measure such that mu n converges to mu. Right? The compactness means this. If you have a sequence, then you can extract a subsequence which converges to some limit. Now, large deviation compactness says exactly the same property for the property of large deviation, which is something more complicated than passes to limited metric space. So, theorem. It says that let psi n be a sequence in sequence of random variables in Px. Sequence of random variables in Px, which is our space X calligraphic. Then there is a subsequence of natural numbers, and there is a lower semi-continuous function I of X 0 plus infinity, such that you have large deviation along this subsequence, except that you cannot divide by 1 over k, you need to divide by 1 over nk. And I write it symbolically like this. The limit as k goes to infinity, 1 over nk logarithm, take any Royal subset in X calligraphic. Right, so take the Borel subset of the space of measures. Normally, probability psi n belongs to gamma, psi n k belongs to gamma, and this is equal to the dot graph minus I of gamma. Okay, so large deviation compactness theorem says that you should consider the spatial frequencies in this space Px or compact metric space, then it is compact in the following sense. Whatever your frequency, you can find the subsequence and the logarithmic continuous function such that along that subsequence you have exactly the relation which was there. Here we recall that this dot means that we have a large deviation up or down and a large deviation lower down. Well, let me first give a corollary on this. Corollary. Probably I will start just to tell you that this is not something very mysterious. Example. Let's assume that we are in a simple situation. So this situation cannot happen in this setting because even if X is finite, you still have simplex here. So this X cannot be finite set. But this result is true in any case, no matter what the nature of this space is. I mean, in fact, I didn't even use this Px. You can think of a sequence which range in any compact metric space X. And I'll just apply it in this particular case. But this particular choice is not important. Okay, in fact, I didn't. The rest of the statement does not even use this. Okay, so let's consider the case we started yesterday. X1, Xn. Use the blue color. X1, Xn. Then we know that large deviation in this setting is finite to many, is a set of finite to many relations, right? So psi n satisfies LDP, even only if you have the following limit n goes to infinity, 1 over n logarithm probability that psi n is equal to xj is equal to minus I of xj. And this should be true for j between 1 and n. So if you have a finite set, a large relation means exactly the set of these large n relations. Now it's obvious what we need to do. We have these sequences. We have the sequences A, n, with index j. So these sequences, so these are the numbers. A, n, with index j. So these are negative numbers. So we have n sequences of negative numbers. Of course, we can choose a subsequence. There is a subsequence nk such that for aj this a nk j converges to limit which I denote by aj. So this is a negative number, so I can write it in the form minus function I on xj. So by definition, I or aj is equal to minus ij. So this is the topology. We just want to have the same notation as there. Okay, so you have finite finite sequences. Choose a subsequence which converges to something. If they define it correctly, it converges. Therefore, in this case of finite space, this large relation compactness is a trivial result. In the general case, roughly speaking, you do this on counter domain sets and then prove that it is sufficient to have upper and lower bounds. So I'll show this some steps of the proof, but now let's discuss the corollary of this result. A corollary from the theorem. So here I consider general state space X. So let psi n be a sequence of random variables in X for which there is a lower semi-continuous function I from X to plus infinity with the following property. The version that I told you also here was do I use this px here? So here it is not used, but in the probably it is just a second. No, in fact I don't use it. So it's fine. So for which there is lower semi-continuous function I with the following property. Here is the property. If nk is a subsequence and lower semi-continuous function j from x 0 plus infinity are such that we can give a number here. So we think have a number, so it's number 1, such that one holds with I, so I have an I here, but I want this to go with j. Painful. Then j is equal to 5. Sorry. What I want to say, so suppose that I'm going to replace here I by j. So condition is that suppose that nk and the lower semi-continuous function j are such that you have this, you have our deviations, but now you have this relation with j. Then dj must be equal to this function. Just once again, you have a sequence, random sequence in X, and you have lower semi-continuous function I. They are fixed. What I asked in the following, if a sequence satisfies large deviation for a principal large deviation relation or with some lower semi-continuous function j, then the j must be equal to this. Just lower semi-continuous function. Fixed. There will be just 1 minute. Okay, so this will be clear. Once again. And then LDP holds for psi n with the right function I. Okay, let me repeat once again what this program is about. This is almost triviality, So the formulation is more complicated than the idea of the proof. But this is very, everybody knows in the case of sequences. If you have a sequence, you call it a bounded sequence. Suppose that any type of sequence which converted to something, that limit will be the same for all of them. Then all the sequences converted to it. This is exactly the same, and the proof is exactly the same, because there is no difference. We have compactness, because we know already that this is the largation or compact set. We have largation. And the property is exactly what you need to say that this must be the limit. Okay? Well, the conclusion is that if the important conclusion is that if for your sequence, in one way or another, you can identify the rank function which will govern large deviations for any subsequence which satisfy that property. Then you have large deviation for the sequence. Okay? Yeah, don't hesitate.
Maybe I misunderstand. Isn't it like there is no other function of subsequence?
Yeah.
Only that. There is nothing else. You cannot find any other J. of
Yeah, so
subsequence.
if as soon as you have large deviation, then it must be equal to 1. Think of sequences. Think of sequences without any remaining and so on. If any subsequence converges to a limit, if you know that for any subsequences, the limit must be equal to the same part, same number, then the entire sequence converges. This is exactly the same thing.
Can you reduce it to that?
Sorry?
Can you reduce it to that?
Essentially, yes, but this is how we say it. Due to my contradiction, suppose that this is not true, then there is gamma and there is stuff and so on. That's exactly the same.
This out of the version.
Yeah, it is important in the compactness, a lot of compactness here. Okay, so let me now give some ideas about the proof of this theorem. And here the proof. Well, now we have a lot of sets, not just minus many, so we need to choose the right family. So let us denote by xj a density dense sequencing in X, and let me denote by rho I decreasing sequence of positive numbers going to 0. All of them are greater than 0, and rho I goes to 0 as I go to infinity. I consider the following family F, which consists of all open balls centered at xj of radius rho I. Ij greater than or equal to 1. Basically, this is a base of topology. Right, so now I do exactly what I did for sequences. Obviously, there is a subsequence nk such that for any ball in the sequence, the limit exists. And I denote that limit by minus j of b. So this is just a notation for j of b. J of b is a step function. It is a function of f, and it is defined as the minus of this limit. If I take the full sequence the limit may not exist, but then I can take subsequence using diagonal process to find the increasing sequence nk such that this limit exists. For the moment, I don't have a rate function. How will I define that function? Let us take any point x, and let us take goals in L, a sequence in F, which is increasing, and the intersection is just this point x. So this is very natural thing to do. You want to define your function I, and you know that it goes to be continuous, so you choose a sequence of goals, increasing sequence of goals. With only intersection in this point x. And then you define I of x as the limit of j of BL. So L goes to infinity. I think there are several things to prove. And obviously, this G day is a non-increasing function of set. Because the larger the set, the larger probability that I could Q minus, therefore the smaller j. Right, so this is a non-increasing function, non-increasing sequence of, well, this is always negative, j will be positive, of non-negative numbers. So therefore, I, not therefore, I, this limit exists if you choose BL. Another simple argument shows that in fact it does not matter which sequence BL you choose, because this is always right. I is well defined. The second property, again, not difficult to prove, I is lower semi-continuous. You just take do the one natural thing to do. You choose take a sequence, and you just prove that the limit will satisfy the right inequality. And finally, for any b in this set F, I cannot compare this I with the function in J, because J is a set function, I is a function of X. I can calculate I on B on the set of this family F. Then again, not difficult to understand that this is always greater than J of B. Because you go to the maximum and well, anyway, all this is simple exercise. Well, now we have a candidate for the right function. So we need to prove those two inequalities, deviation upper and lower bounds. So let me prove the lower bounds, and the upper bound is exactly, well, not exactly, it's similar argument using in addition some compactness property. Okay, let us prove large deviation lower bound. Now, what I need to do, I need to take set G, which is open, and I need to prove that the limit as k goes to infinity, well, limit inf, as k goes to infinity of 1 over nk logarithm probability that psi nk belongs to G is minorized by minus I of G. Now, one trivial case, I of G may be equal to plus infinity. In this case, there is nothing to prove. So this is plus infinity minus infinity is minus infinity, and everything is greater than minus infinity. So let's suppose that I of G is finite. In that case, well, I of G is the infimum of I on the set G. For any epsilon, I can find x epsilon in G such that I of x epsilon. I need to put the right inequality. So this is the smallest. So I x epsilon will be smaller than I of g plus epsilon, right? Because I of g is the infimum over g. If I fix epsilon and take something which is slightly larger than infimum, I can find something which is smaller than that. Okay, so this was my set G. This is x epsilon, which is almost the infimum. Now, what is the definition of I of x epsilon? I of x epsilon is this limit. Is this limit. Therefore, I can approximate I of x epsilon. Sorry, I need to do one more step, probably. Just 1 second. X epsilon. No, I don't want to do anything. I just do this thing for this relation. So there is B in F, B epsilon in F, such that I of x epsilon is smaller than I of x epsilon is what I want is the following. So this is a decreasing sequence. Sorry, this is a non-decreasing. It's not non-decreasing. This is a non-decreasing sequence. I'm sorry. DL is a decreasing sequence. Therefore, this one is a non-decreasing sequence. This one is non-decreasing sequence. Therefore, I can find D epsilon in F such that I of J of B epsilon J of B epsilon will be bigger than I x epsilon minus epsilon. Right? Because this goes to Ix, which is the large value. Then I can approximate by this. And now I can write, I can use this to write the inequality. So the limit, the low limit, as k goes to infinity, 1 over nk, lowering probability that sin nk belongs to G. Yeah, and in addition, I can assume that this B epsilon is in G. Right? Because rules shrink to X, so I can always assume that this is included in G. So the probability that psi and k is in G is greater than lim inf as k goes to infinity of 1 over nk logarithm probability. I replace G by B epsilon. Right now, this limit exists according to my choice, and this limit is equal to minus J of B epsilon, according to this choice of sequence nk. Now, J of B epsilon is what? J of B epsilon. Sorry, we need to use this inequality because that one is not right one. G of B epsilon is this. G of B epsilon is time minus it. It will be greater than I of B epsilon. But probably we don't need this. We just involve in the continuity of I. I of B epsilon. Growth in continuity implies that I of B epsilon, if this ball is sufficiently small, I of B epsilon will be what? Will be smaller. No, will be bigger than I x epsilon minus epsilon. Right, so we don't need this. I'm sorry. This is not needed. This is needed for upper bound, but for a lower bound, we need only this. We choose B epsilon, such that we have this inequality, and this is possible because I is lower than the continuous. I'm now completely confused. You don't even need this. Because I of B epsilon, it is smaller than, it is certainly smaller than I of X epsilon. You don't even need this. And therefore, with the sign minus, this will be bigger than minus I of X epsilon, and minus I of X epsilon is greater than minus IG minus epsilon. I'm sorry. It's, I choose to prove the lower bound to avoid complication which appears in the upper bound, because you then need really properties to use. So this one is real trivial. So we don't need anything. We don't even need the loss and continuity of I. Just do this estimate. So once again, so you have this because B epsilon is included in G. So you take any B epsilon inside G. B epsilon in F, which is inside G, and that's it. We don't need anything else. We need only this. So you have this limit exists, it is minus G epsilon, because G is smaller than I, so this is greater than minus I of the epsilon. I of the epsilon is smaller than I except for because this is bigger, and therefore the sign minus is bigger, and this is according to our choice of X epsilon, you have this. And because this is true for any epsilon, you have the lower bound. This is not everything, but that is what I think what's trying to do. So this proves the lower bound, and for upper bound, you need to work a bit more using compactness of your closed set. Because we are in a compact set, you need to use compactness. Okay, so now this is the end of the first section, I guess. Now we'll move to more interesting stuff. This is.
Sorry, excuse me. The online screen is very blurry. Can you help me adjust it?
Which one is blurry? Sorry.
The technician will start.
Okay. Yeah, it's okay. Well, this is the second section. It is called Kifer criterion. We will assume that we have a compact vector space X. In our plane space X, calligraphic is the space of measures of this compact vector space. As you know, this is a compact space. And our goal is to find sufficient condition for a sequence of X valued random variables to satisfy our relation principle. So we want to have a lower semi-continuous function I from X to 0 plus infinity, such that for any gamma, you need to have the limit as n goes to infinity, 1 over n, logarithm probability, mu n in gamma, which is equal with the dot about minus I of gamma. So what we know already. We know, according to large deviation compactness, that we can find a subsequence for which large deviation holds. Or we know that if in one way or another, we can say that any subsequence for which large deviation holds must have as a range function one single function, then we can conclude that large deviation is true for the sequence domain. What we know also is that you have contraction principle. if you know large deviations for this new n, and you apply continuous function from this space X to another space, then the resulting sequence will also satisfy large deviation principle, and for the rest function we have the exact formula. So let me describe some heuristics how we can understand the Kifer criteria. Now let's begin with a well-known result, which concerns the finite dimensional case. So let's suppose that X is a subset in RD. Okay, let's assume that X is a subset in RD. So we have a sequence of RD valued random variables. And we want to understand what are the sufficient conditions for the validity of LDP. In this case, there is a nice result called Gaussian theorem. It says the following. Well, we know already, I erased it, but this pressure function. So suppose that for any alpha, in RD, the following expression is well defined. The limit n goes to infinity, 1 over n, logarithmic, exponential, expectation exponential of n alpha zeta n. So there is Q alpha, and Q alpha is differentiable. For any alpha. Then LDP holds for zeta n with the right function, which is Legendre transform of this Q alpha. Holds for zeta n with right function I of R, which is the supremum, and alpha is in RD, R alpha minus Q of alpha. Okay, let's see what this theorem is about. Recall that according to one lemma, if you have LDP, then this Q alpha is well defined, and it is the Legendre transform of the right function. This was the variable lemma we started with today. If you have LDP, you have Q alpha, which is the right function, which is the Legendre transform of the right function. Gaussian theorem says goes in the opposite direction. It says that suppose this function Q alpha is well defined. It is not sufficient for the LDP. But it says it suffices to have differentiability, then you have everything. Not only the LDP holds, but it's also this I, which is the Legendre transform of Q alpha. In particular, it is not only also continuous, but also convex. According to Varela lemma and some convex analysis, to recover phi, you need to know not only the continuity, but also convexity. In that case, you can recover phi from Q alpha. Gaussian theorem says that suppose that Q alpha exists, and it is differentiable, then automatically a large deviation in this rate function, which is convex. Okay, so this, I will not prove this theorem. You can find the proof in any more or less advanced book on large deviation. For instance, you can find the proof in the book of Richard Ellis. called entropy, large deviations, and so on, or any other one booking, well, not really one, any other book of large deviations which goes sufficiently far to prove Gartner's theorem. So this is true for this is for finite dimensional case. I cannot apply this result in my situation because in my situation this X is finite dimensional only if this set X is finite. If this X set X briefly, then you never have finite dimensional space of vectors. But let us consider the following family of functions. Let us fix gamma, which is a finite set in the space of continuous functions. I take any finite set here. And then I consider a function phi gamma, which goes from Px, which is my space X, to Rd. Sorry, this should be Rd. This is the same as here. Okay, I have a function from Px to Rd, which takes any measure of mu to the integrals v1 mu, vg mu. Right, so the function from Px to Rd, and obviously this function is continuous because I have a Richter topology here. If measures converge, then the integrals also converge. So phi gamma is a continuous function from X to Rd. Now, suppose that Nk, a subsequence, is such that mu Nk satisfies LDP with some rate function which I denote by I. I know that such thing subsequence exists, but it's not important that it is. Suppose that I'm trying to find the corollary which was there. I'm trying to show that if you have a subsequence which satisfies LDP, then the rate function does not depend on the subsequence. So suppose that there is a subsequence which satisfies LDP with a rate function I. Then, according to contraction principle, phi gamma for any gamma, phi gamma mu nk satisfies LDP with a rate function which can be written as follows. It is I gamma of, now we have a function defined on Rd. We have a function Rd. I gamma R is equal to the infimum of I mu such that phi gamma mu is equal to R. Or in other words, I have I, this function I, calculated on phi gamma minus 1 of R. Okay, contraction principle, the very first result of studies, says that if you have a sequence satisfying LDP and we have a continuous function, then the image also satisfies LDP and the rate function is given by this relation. I call it contracted rate function. Suppose now, I think I'm right on the other side. No, right here.
Space here.
Sorry? Yeah, there's space there. Okay. Well, suppose we manage to prove that phi gamma mu n satisfies the hypothesis of Gardner-Ellis theory. Okay, suppose that we know that those measures, phi gamma, well, phi gamma nu AK satisfies large deviation because of fraction principle. But suppose that for by some chance, at least for some set gamma, I can prove that this phi gamma nu n satisfies the large deviation principle due to Gardner-Ellis. So if we have large deviation due to Gardner-Ellis, which means that you have the properties of Gardner-Ellis theory. Then, according to Gardner-Ellis, I can write explicitly, well, not explicitly, but I can write the range function in terms of legitimate transform of that function Q. So let us write that. So let us denote by J gamma range function. So J gamma of R will be the supremum over all alpha in RB, R alpha minus Q gamma alpha. But what is Q gamma alpha? Let's calculate Q gamma alpha. Q gamma alpha is equal to the limit as n goes to infinity, 1 over n logarithm in value exponential, and I need to take R. I need to take alpha, and then P gamma, phi gamma of R, phi gamma of UN. Well, we're trying to see what it gives. What is phi gamma nu n? It is B1 nu n, B2 nu n. So written here is the limit as n goes to infinity. Oh, you need to have some patience here, but not too long. Logarithm in value exponential. So what we have here? We have n, and then I have alpha 1 B1 nu n plus, so there is no comma here, but there is bracket here. I'm taking the scalar product, right? Plus alpha n to alpha b b d nu n. Okay, so according to Gardner-Ellis theorem, I need to take scalar product of alpha with zeta n. Who is zeta n? Zeta n is phi gamma of nu n. Who is phi gamma nu n? It is V1 nu n, Vd nu n. So what is written here is exactly this scalar product. I show you. So this bracket is a scalar product in Rd. This bracket is the integral of x. But now I see that we have always the same measure here, and I can put this alpha 1 with V1, alpha b with Vd, and take the sum. So what you get is the following. The limit n goes to infinity, 1 over n logarithm in value exponential. So I keep this n, and I write here as B alpha in value with nu n, where B alpha is alpha 1 B1 plus so on plus alpha D BD. And the conclusion is that this Q gamma alpha is essentially a limit of something which can be expressed in terms of this measure nu n. So this is universal. It does not depend on gamma. It depends on gamma via this D alpha. Okay. Now, if we put, if we compare this formula with the other one, I know that this sequence satisfies our deviations, but there is a subsequence that also satisfies our deviations. And for that subsequence, I have the exact formula for the rate function. So it gives the following, because the rate function is unique. This is one of the exercises we discussed. Conclusion is the following. If by chance I know that this phi gamma you can satisfy the hypothesis of Gauss theorem, then necessarily you will have that I gamma of I of phi gamma minus 1. Phi gamma minus 1 R is equal to this supremum. Alpha D R alpha minus Q gamma alpha, which in fact Q gamma alpha depends on gamma only by the function below. Okay, so just linear combination alpha on one alpha BD, and we get the supremum of alpha, so you really see only the function B alpha. So you have this relation for any subsequence which satisfies large deviation principle. The idea is the following: if you have sufficient limits, and this is true each time for any finite subset of Cs. This is true each time you can prove Gauss hypothesis for the sequence phi gamma you take. So you have a lot of relations for the function I. So if you have sufficiently many, you will be able to determine this function uniquely, because what it frequently does not depend on gamma. It is a legitimate transform of something, and we'll see very shortly that this Q gamma alpha, in fact, it is the function Q, which was written in before, calculated on the function B alpha. Because it is essentially here. You recognize this function, that this is exactly Q of B alpha. So you have, if you have sufficient range in this type of relation, then you may hope to have uniqueness, and this will imply the relation sequence. So this is the idea. What I will do now, I will formulate Kifer's criterion, and we'll have some time also to make this claim more specific. What really I need to prove to have the uniqueness of the rate. Thanks, Ross.
Here's a question.
Yeah.
For this contraction theorem, you said this Px is not necessary. You could choose another compact symmetric space, right? In the theorem.
No. In Kifer's theorem, I will use this structure of P and so on.
You use this, yeah.
Yeah.
You use this
Well,
integral, yeah.
it can be extended to various situations, but essentially this is what I think. Yeah. Okay, not one optical theory. Then it was through by Kifer, 1990. Well, it is just a formalization of a lot of knowledge which was accumulated before the result, but he made it somehow to exactly single out the single conditions which can be applied in different situations. So let UN be a sequence of Px valued random variables satisfying the following two properties. For a dense subspace which has graphic Cx. Okay, so I have a sequence of random vectors, and I have a dense subspace in this space of continuous functions. So there are two conditions. The first one is existence of pressure, as denoted by EP, which is existence of pressure. And it comes from here. I mean, you want this Q gamma alpha exists for sufficiently many gamma. Or you want this expression to have a limit for sufficiently many functions of that form. And those functions must be sufficiently large, sufficiently many to ensure uniqueness here. To ensure this, that this implies uniqueness of I.
This is X compact case, right?
X is compact. This X is compact and Px dot because X is. So I always consider compact. I don't consider uniqueness. So existence of pressure for any V in this set, in this subspace V, which is dense, there is this QV, which is the limit as n goes to infinity, 1 over n logarithm mean value exponential n v mu n. Well, to formulate the second condition, I should have done it earlier. Formulating the second condition, I need some concept which is called equilibrium state. Remember that we had this inversion formula for QV. Well, we had first the Gaussian transform Q. Q is a convex one which is function. We can define the Gaussian transform I of U. Yes. I mu over V in Cx V mu minus Q of V. So this is the Legendre transform of Q, and by inversion formula, we know that for any V, you can recover it by essentially the same formula, V mu minus I of mu. Okay, so these are back from convex analysis. Now, using the compactness, it's not difficult to show that this supremum is in fact achieved. You do the most natural thing to do. You choose a sequence which goes to the supremum. You use compactness. Well, okay, lemma. Let us formulate as a lemma. Anyway, I won't be able to do anything after this, so there's the details here. The lemma says that for any V, there is mu such that you have equality. To V is equal to V mu minus I of mu. So let me know this relation. I think I didn't use any numbers for this relation too. So definition: any mu satisfying two is called equilibrium state for V. Let us say that for any V, there is at least one equilibrium state. Well, ideal of the proof. Let mu n be such that, well, this expression goes to the supremum. V mu n minus I mu n goes to Q of V. Such a sequence exists because by definition of supremum, since Px is compact, we can assume that mu n converges to something. Converges in the big star topology, of course. Since I is lower semi-continuous, the lim inf of I of mu n is greater than I of mu. And therefore, if I calculate this, the lim, now this is lim inf, I take the sign of minus, it will be lim sup as n goes to infinity, V mu n minus I of mu n. This will be, this was greater, this will be smaller. V mu n converges because mu n converges to V mu. And this converges to is minor I by minus I of mu. So this expression for the limiting measure mu is greater than the lim sup, but on the other hand, this limit exists and it is equal to Q. So QV is smaller than this expression, but it cannot be larger than therefore this equal. And because QV by definition by the inversion formula is supremum. We have proven that for this mu you have something which is larger than supremum, it cannot be larger, therefore we have this equality. This is the full proof. The equilibrium state always exists based on the compact case. Now the second condition, the uniqueness of equilibrium state, says the following: the uniqueness of equilibrium state. It says that for any V, there is a unique equilibrium state UV. Then the LVP holds for UN with the range function I of nu, which is given as the Legendre transform of the function Q of V. Well, this is the Kifer theorem. Basically, we have two conditions which are at least easy to formulate. It's not always easy to check their validity, but at least formulation is easy. Now the idea is exactly what I mentioned there. So let's say that, for instance, there are two conditions in the Gaussian theorem, right? So we have existence of pressure and differentiability of the pressure. So in fact, these two conditions are exactly those conditions, because the first one is existence, and the second one, uniqueness of equilibrium state. This equilibrium state is the point which saturates the Legendre transform. And it is well known that when Legendre transform is saturated at only one point, then at that point it is differential. So yeah.
So in finite dimension, Kifer reduces to Gartner limits, right?
Indeed, yeah. In finite dimension, it is indeed, yeah. If you have X finite state, it is exactly Gartner state. Yeah. Well, now let's see. We have a couple of minutes. Let's see why the first condition is Gartner theorem is follows from here. Because what was the condition in the Gartner theorem? Existence of Q gamma alpha and differentiability of Q gamma. Now the thing is that existence of Q gamma alpha is just existence of the pressure, and it was almost done here. So we need to prove the existence of Q gamma alpha. And Q gamma alpha, according to the formula of the battery, here, Q gamma alpha. Q gamma alpha is the limit as n goes to infinity of 1 over n logarithm mean value exponential n b alpha mu n. But this is exactly Q of the alpha. And B alpha is of course in B calligraphic because B is a vector space. And it is indeed important not only that this B calligraphic is dense, but it should be vector space. Because when I define Q gamma alpha, I need to take B alpha, which is a linear combination of some element of B. And since B is a vector space, this B alpha will be an element of B, and according to the first condition, in B, this limit exists for any finite set gamma in B, and for any alpha. Okay, so the first condition in the Garfinkel's theorem is just a straightforward consequence of this explicit formula and the first hypothesis in Kifer's theorem. What is, in fact, it is not that difficult, it will be very quick. It is the idea that if you have a convex function, if you fix a point, if you have a convex function, then differentiability in some point alpha, in the one-dimensional case, so you fix a point alpha, and you want to understand if this function Q alpha is differentiable here. Differentiability is exactly the uniqueness of it is exactly the fact that the sub-differential consists of single points. So let me recall that if you have a function Q which is complex, then the sub-differential the point alpha is the set of those R for which Q beta minus Q beta is larger than Q alpha plus R beta minus alpha. In other words, you take a straight line with a slope R passing through this point. Convex function may not be differentiable. In that case, there will be a lot of vectors like that. So sub-differential convex function is this a set of those slopes for which the function is greater than the straight line passing through this point in the slope R. So this should be for any true for any beta. Now in the one-dimensional case, it is obvious that Q is differentiable alpha if and only if this sub-differential is a singleton. Which means that it is differentiable. There is Q prime alpha. So the second condition in Kifer's theorem ensures that this differentiability is true for any function Q gamma alpha if gamma is a finite set of B, and we will start this next time. That's it also.
Do you have questions?
Yeah, just maybe I missed it. I was thought that this V here, this vector space, has any specific assumptions?
No, just a vector space which is dense in CX.
Okay.
Any space.
So for Gardner-Ellis, so what kind of stochastic ODE, to which kind of stochastic ODE you can apply Gardner-Ellis?
Well, Gardner-Ellis, if you really want to have for empirical measures, then I'm afraid you cannot, because it is about finite dimensional case.
Yeah, ordinary.
Yeah, I understand, but finite dimensional actually, this calligraphic actually is finite dimensional, right? You know that. This calligraphic X, where your n variable 3 should be finite dimensional.
Yes.
And that is finite dimensional only if your state space is finite.
But yes. So
I mean, maybe you're talking about Kifer, right?
no. Gartner is
You know, the Gartner analysis is about the case when this X calligraphic is finite dimensional. You agree with that?
yes.
And then to find this X to be finite dimensional, your X normal should be finite. Basically, you need a process on finite. This applies to finite state homologies. You agree with that? Yeah.
And you are going. You have this example, right, in mind.
Yeah.
I am going to apply keeping the for that example.
For that,
Under some conditions on the vector fields in the equation.
yeah, I can see a simple situation where the vector could generate everything.
Okay.
Even in that case, I need to verify.
Okay. Interesting. Okay. Looking forward to that. Thank you very much.